Hi there, welcome back to Petrophysics Rocks. I'm working on trying to get some shorter content out there, a bit more manageable stuff, more bite-size type videos. I've got the video down to, well, it's still over half an hour, but I'm working on it. So I thought I'd try and create some maybe some shorter videos, which I'm going to call a series called Petrophysical Tips. Now, none of it's particularly new or advanced or innovative. But it's something that I've encountered throughout my career, some mistakes that are commonly made in various areas. And so I thought I'd try and put together some short, crisp presentations and a tool I've also created to help you work through it. So if you want to email me at the link down below, there'll be an email for this particular spreadsheet that I've put together. This presentation and the spreadsheet is all about sums and averages. These are the average properties that appear, that we calculate on the bottom of our log products or whatever, and then we hand them over to geologists and reservoir engineers, and they stick them into Excel spreadsheets, and they average them, and they try and come up with various reservoir properties from tables of Excel numbers. So there are some pitfalls that are commonly made, and I've hopefully highlighted those on the way here. So if you'd like the spreadsheet at the end, as I say, send me an email at the link below. Otherwise, give me a like and a subscribe, and maybe write in the comments down below the sorts of things you'd like to see. I've got another one in this petrophysical tips, PP tips series on its way. But for now, let's get on with reservoir sums and averages evaluation. It's something that's a little bit trickier than you might think, and it's something that we often get wrong. Okay, so thanks. See you next time. Cheers. This presentation is called Reservoir Sums and Averages Evaluation. As petrophysicists, we are frequently asked if we can predict the range of oil field properties from the range of well log properties that we derive, our reservoir sums and averages for each well. Can we use that data set to predict the range of the size of oil fields that we're interested in developing or appraising? And the problem arises obviously that the range of oil field properties is not the same as the range of well log properties, but there is a way that we can get one to the other through a mathematical methodology that I'm going to show you now. It's called the confidence in the mean, and it's an Excel implementation that I've got here. And if you send me an email at the link down below, I'll send you the spreadsheet, and you can sit in a dark room with a cup of coffee and work out what I've done. But hopefully, combining that with this presentation, you'll be able to see what the issue is. Our reservoir, our management are obviously keen to know how big the oil field could be, how small it could be, and whether we've got enough to go ahead with the development. And to predict that from the well log averages is a tricky thing that is often misused in Excel spreadsheets. So I'm going to show you some common mistakes to make that I've encountered down the years, and hopefully this will provide you with a bit of insight how to tackle this sort of a problem. Okay, so what I'm going to do now is I'm going to take you through a presentation, and one of the things that I'm going to use is an oil field in the North Sea. Again, it's an abandoned oil field, if you like. It's ceased production now, and we're going to go back in time to 1978-ish. And then sort of take the first 7 or 8 appraisal wells and see if we can predict what the eventual average properties will be after some 65 wells later. We've got access to all the data, so this will be like a little mini test of this technique, if you like. And as I say, hopefully you can go through the spreadsheet afterwards and see all the mistakes that I've made. Okay, and then I'll hopefully explain it to you in this sums and averaging process. Okay, so what I'm going to do is, as usual, just paint my background. These are the companies that I've worked with and the organizations that I've worked with as well. And that's probably enough about that, because you've probably seen all the other all the other presentations that I've made as well. So what we're going to do is I'm going to show you back in the North Sea, this example oil field up here in the UK sector. These are all the sort of areas around the world, the basins that I've worked in, but we're going back to the good old North Sea, where I've got this released data set from the NSTA, the North Sea Transition Authority, and I've been able to analyse all the wells, and we're going to group them in such a way that we can make an estimate of the average properties from a limited well data set. Here's Hutton oil field up here in the northern North Sea. You may recall from my last presentation, Nelson was down around here. I did a thin bed analysis. It's down there. So this is a bit further north, a bit north of Shetland, probably deeper water, and it was a tension leg platform, more of which later. But if we kind of zoom into where we are, we're in the BRENT province, if you like, some good old famous North Sea oil fields like BRENT, Ninian, Cormorant, Magnus up here in the far north. These are all famous North Sea oil fields in the BRENT province, and more about that later. So this particular information from the NST website says that the field was discovered in 1975. I think one of the wells was from 1973 though, so skating over that data. We're going to zoom in a little bit to Hutton and its near neighbour Northwest Hutton. Hutton is the shallower oil field. It's a bit nicer, a bit more forgiving. Northwest Hutton, although aerially larger, goes a lot deeper, and there's a bit of a problem with deep Brent reservoirs with illite in those reservoirs. But if you like, we're going to concentrate on Hutton, the easy one, if you like. And if you look at that was just this was just the kind of like the field outline from the NST website. But if you dig deeper and look at a depth structure map, so if I open this up from my good friend Mike Cooper and bring this over, here is the Trove data set. Basically, what Trove does is it just captures all the information from the public domain that Mike can get his hands on, and his team there put this stuff together. It's got some useful reservoir properties and descriptions about some of the issues about various oil fields in the North Sea. He lent me this Hutton one, and I think one of the data sets here is porosity. It tells you that the temperature, pressure, field size, bubble point. Where are we? Here's the porosity is the porosity range is 22%. The average porosity is 22%, and I think we can all agree that the average is just one number, but it does also give you a range here, 17 to 26%. So that's Trove. If you're interested, I'm sure if you contact Mike Cooper, I'm sure he's got a YouTube channel. I'm sure you can come to an arrangement with him. Any fields that you're working on, he's got a whole database of publicly released data. Okay, so just shut that down now. So this is Hutton, the depth structure when you look beyond. But going back, here is the TLP. As it was in the day, the tension leg platform. It's deep water stuff. So this is it's kind of like a semi-sub, but it's tethered to the ground with tension-legged stuff, engineering stuff. It probably looks more like that these days, obviously because it's been abandoned. And I think it was towed off site in 2001. The TLP was removed, which means that so it was towed off site in 2001, and it probably looks something like that now. So this is the TLP, but what we're interested in as petrophysicists and subsurface people is what goes on down below the surface. This is the first development well in 1981, in fact. So this is H1, and it was drilled before the platform got there, actually, from the Dundee Kingsnorth. And as I say, it's a typical Brent sequence log of the famous Brent formation in the North Sea. It's made up of the Broom, the Rannoch. Let me get my highlighter on it. The Broom, the Rannoch, the Etive, the Ness and the Tarbert, a bit of beach sand over the top. And this fluvially dominated Ness stuff, Ness channels, kind of like an upper shore face Etive, a lower shore face Rannoch, and submarine sands, the Broome. So all that together is the BRENT formation. And what I'm going to do here is I'm going to have a look at these are the sums and averages on the bottom of these spreadsheets of these CPIs, and we're going to just take this this BRENT formation. So the whole lot. I'm going to take all these BRENT averages. I'm going to take them from the first 10 appraisal wells. So this is just that BRENT zone, that composite zone, and I've got some TVDs, subsea, tops, bottoms, gross, apparent vertical thicknesses, net to gross, apparent vertical pay, hydrocarbon pore volume, V-clay, shale volume, if you like, a total porosity, and over the net and over the pay, and the saturation over the pay, and a predicted permeability too. So this is as we were in 1978, I guess, or something, the appraisal program. So with these 10 wells, can we predict what the final average porosity is going to be? So afterwards, we've got I'm going to take another data set, which is those 10 wells, and I'm going to add the first 10 pre-development wells. There's the H1 well that we just looked at there. That's the first of the production wells, and as I say, it was pre-drilled before the platform got there. And then we're going to look at the final answer with 65 wells worth of data here, and see whether we can predict the range of average properties for the field as a whole using these data sets from these 10 first appraisal wells. Okay, so we're going to take these sums and averages. This is just 10 wells here, and we're going to put them into Excel, and I'm going to chart them up so that you can see this is the net to gross, this is the porosity histogram, and this is the hydrocarbon pore volume. So that's the volume of oil, if you like, in porosity terms. So if you took that and divided it into that, you'd get the oil saturation and therefore the water saturation. And this is the net to gross, the proportion of sand, the proportion of reservoir to shale sort of stuff. And in here we've got the simple Excel averages, which is what most geologists kind of come up with when they first do this sort of stuff. They take the well log averages that the petrophysicist has given them, and then they just sort of take the Excel average property, and they take the average, in this case the top depth, the average top depth, 10,340 feet, and then similarly with the net to gross, you could take the average using this Excel average function, and similarly with water saturation, you just the average of this column here. Now I'm going to explain to you why that's not the right thing to do, but I just put it in here to illustrate the point. It's a common mistake that I often see made, that those averages. Now I guess if everything's the same thickness and the same on the net to gross, then you can get away with doing some of this stuff. But where you have variable thickness and variable net to gross, then it's dangerous just to use the Excel averaging. But similarly, you can use the Excel functions to predict a standard deviation, P90, a P10. That's the range, the percentile of the data range and the sampling. So let me zoom into that a little bit more. You can see here, so taking this phi column here, so the average is 18.9. Remember, Trove said 22. And then the standard deviation is plus or minus 3 PU, with a P90 and a P10 of 15 to 22. And if you look at that, these are just similar. These are just Excel functions, percentile. So the percentile of this range, and in this case, I've used the 10 percentile. So by convention, most people, and it depends by company. I think or Total used to do it differently or whatever, but P90s in our world are generally the smaller number, if you like. There's the 90% chance you're going to get at least that sort of stuff. But actually in percentile terms, it's the 10th percentile cumulative frequency. Sometimes you just need a cup of coffee and sit down and make sure you're comparing light with light. Depends what your exploration department do. But these are simple Excel functions, and you can see here what I've done is I've fitted a normal distribution and cumulative frequency over the top here, and I'll show you how I derive that. But you can see that this normal distribution doesn't quite match the population percentile P10 and P90. That's because this population is not strictly necessarily that normal. I mean, it's very close. You can see because this percentile lies close to the normal distribution, it's not far off a normal distribution. But obviously, with so few wells, you'd find not many people would believe you, if you like. So that functionality is basically derived from here. So the histograms are created using this Excel array function. Histograms can be a bit tricky in Excel, but what I found is that if you put all the bins here, so 0 to 41 porosity bins, that's the sort of expected porosity range. Don't get many porosities over 40%. And then you use this frequency in our data range. Our table was M5 to M69, you may remember. Over these bin size, it will report back the number of occurrences of this data within this bin. And the tricky thing about array functions is that they operate on over the whole array at the time, and you enter them, and then you have to do a Control-Shift-Enter to make any edits to them, sort of stuff. But you'll see that in the spreadsheet if you get it. Just for those of you who don't want to get the spreadsheet, here's the function, and you can have a play around with creating these histograms. And similarly, to create this normal distribution, you basically take the mean and the standard deviation of your data set, and then use this normdist function. And I think in newer versions of Excel, there's some slightly newer ones, slightly different ones or whatever, but this old version I just use the normdist function, and it basically says, right, okay, it gives you a normalized distribution with this mean and this standard deviation. So the distribution is the bell curve, if you like, is done with a function false, and this cumulative normalized curve is exactly the same function but has the word true there, and then you get this cumulative function. Anyway, so that's how you do that, and then I just put them over the top there, and then I compare how normal is my data. Okay, so that's fine and dandy, just as a basic Excel spreadsheet functions. But really, what you need to do is properly weight the averages. So that's this line here, and I'll just zoom into that. So let's take the net to gross here. The average net to gross, it uses this sum product equation. So the sum product of the G's is the gross times the corresponding net to gross. So that times that, and then divide it by the sum of the gross. So the gross interval times the net interval will give you the correctly weighted net to gross property. And you can see here it's a little bit different. So the Excel average is 63% net to gross, but the actual average, the weighted average, is which accounts for the thickness variations. You see I've got a thin zone here. This zone here is 34 foot thick, and its net to gross is pretty low, 0.39. So you don't want that, you want it to be properly weighted to the reservoir thickness. And similarly, if you go on to porosity, you want the net porosity, which is the sum product of the gross times the net to gross times the porosity, which gives you the pore volume, and then you divide it by the gross times the sine product with the net to gross, with the net volume, and then that'll give you the properly weighted porosity average. And then you can see in this case it's not that much different, because the porosities are all pretty similar anyway. And if we go on to this last one here, the correctly weighted water saturation is the apparent pay thickness in this case times the N, which is the porosity over the pay, times the oil saturation divided by, water saturation divided by the net pore volume, and then you get the correctly weighted saturation. And you can see that's quite different actually. That's 32. That's 32% water saturation compared to the standard XL average of 39. So that's just something to watch out for. It's frequently not averaged correctly. When you get a table of numbers, it's obviously just it's tempting just to do the average, but that's not correct. So anyway, there you have it. You can take it. So if we go back to this this curve here, so you can see I've just adjusted the averages here to use the weighted averages. So that's the that's the weighted averages of this well population. Okay, so the next thing is this confidence in the mean function. So I put this little Excel help note in here as an aide memoire for you, and you can read all about this function. It's basically, if this is the range of average well properties, how confident are we that this average property will be the average for the whole population? And that's what this confidence in the mean is. And you can see that that's the range of well properties, and then that's the range of expected means, if you like. So of this population, I think that the average property of however, if I added more wells, would still be within this range. If I added more, so this is the range of well properties, and this in essence is the range of field properties. That's the assertion that I'm making here. And again, similarly, I can here's the function. The confidence in the mean is basically you're 80% confident that your well average properties, your field average properties of these wells, this population average, is going to fall within this confidence range. And then we can calculate a P90 and a P10 based on this average plus or minus the confidence level either side. That will give you your P90 and the P10, which means that you're 80% confident that the mean is going to be within this range, because there's going to be 10% higher and 10% lower outside that range. So that's basically what we're saying here, is that we're 80% confident that the mean is going to fall within this confidence range. We can back calculate a standard deviation from that, the difference between the P90 and the P10, or sorry, the P90 and the mean. We can back calculate that, assuming it's a normal distribution, and by definition, this is a normal distribution. We've defined it so by using this multiplier. Again, it's probably sit down with a cup of coffee in a darkened room to work your way through it methodically, if I've gone through it a bit too quickly here. But basically what we're saying is that we're going to take this data set and I'm going to put both distributions on. So this is the distribution of the wells, and this should be the distribution of our expected population means, if you like, the average properties for the field as a whole. So if I zoom in, so I'm just basically going to take I'm going to take these 10 data sets down here. So this is the first 10 wells, the appraisal wells, and so therefore by definition I'm 80% confident that the mean of this population is going to be within this range. So then we can add in our first 10 platform wells or pre-development wells, and so we added in 10 wells. We've now got 21 wells in our population, and it's not looking too good. The average properties have skewed a bit outside our range, so that's not so good. And we add in, by the time we get to all the development wells, all 64 wells, 64 wells, we're outside our range. So this technique doesn't work. We can't predict what the average property is going to be. So this again kind of comes back to another common occurrence of an issue that I find, is that if we go back to the beginning, one of the things that I find is that a common mistake to make, even though we've got an HCPV uncertainty of plus or minus 7%. Basically, we're saying that this standard deviation is 7.7% of the total porosity. Sorry, HCPV calculation. So we've got a 7.7% error. And a common issue that I also see is that engineers in particular and geologists, they just look at tables of numbers and they just do the stats on them, and they just do the maths, and they don't really look at what the data is telling them. So if you cross plot the data, depth in this case, porosity versus depth, you can see there's quite a clear depth trend in this data. And so the spreadsheet will produce a number of QC cross plots that you can graphically check. But I know, because I checked, that the Hutton field itself is mainly in over this depth range, and so therefore this appraisal set has got a couple of deep wells in it that may or may not be representative. So if I basically take out these these deeper wells and leave, so now we've only got 6 wells in our population, and you can see our uncertainties increased to plus or minus 9% now. So, but now I'm 80% confident that the mean will fall within these limits here, although plus or minus a bigger error bar, if you like, plus or minus 9%. So these 6 wells now, because we've got less wells, the uncertainty is increased. So you see, that's with all 10 wells, but removing the deeper wells, that's where I'm now confident that our 80%, I'm 80% confident that the mean is going to fall within this range. Okay, so now we're going to add in our pre-drill wells, and okay, so that's so you see we're adding a lot more wells up here, and then in the final 65 wells, we've got 65 wells here. This is the P90 and the P10 depth range, and the P90 and the P10 porosity range. And you see that our average porosity is, what is our average porosity here? I'm God snowblind. 21.2%. Now, what did Trove say? 22%. So, okay, we kind of got there. Around about 20%. So we stayed within our initial estimate from our first 10 wells to the last 64 wells. Okay, I hope that's proved useful to you. As I say, here's some QC cross plots. It's always good to look at the data when you get a table of numbers. Just have a look at it. Here's the pore-perm relationship, the porosity distribution. There's that depth trend in the average properties for all 65 wells. Is there a slight net to gross trend in there? Well, we'll see. There's a couple of thin thin intervals in here, only less than 200 foot thick, and some less than 50 foot thick, and they've got quite low net thicknesses as well. Here is the spreadsheet. What I'm going to do is I'm going to just open this up and bring it over for you to have a look at. If you'd like a copy of this spreadsheet, the key thing is what I've done is I've put all this stuff here. Here's the confidence notes aid memoir, and here is the confidence in the mean stuff. Here's some QC cross plots. Here's the histogram setups, and you can add in and subtract and hide. So here I've left some space for you. You can add in some more wells for your particular projects, or you can use the hide column functions, the hide row functions, and set it up to be able to print out in your own way. The only tricky thing that I would point out now, and this is why I'm showing you this now, is that oops, where did it go? There we go. Nope. There's the only tricky thing that I would point out now, if I can just reduce that, is this stuff here. So when you put in your well log sum averages, these cross plots are all set up to cross plot with this range over here. So what you need to do is take this top line here. Bum, 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 bum. Now there probably is a slicker way of doing it. So here's this top. This is a row of formulas here. Just press copy, and then copy that all down to here. Copy, and I would copy the formulas, and then you see everything is minus 999s. So when you put new data in, refresh this. So copy the formula down, press copy, paste just the values, then find and replace, get rid of the minus 999.25s with nothing, replace all. Okay. This is an old way of doing things, because back in the day I found that Excel charts didn't like having minus 999s in them, and they didn't have, if you put an if loop in there, it puts zeros and nulls in it, and then it won't let you do cross plots, it just lets you do line plots. So there's that little trick to do, and I put a memoir, copy these equations down, then cut and paste the values only, so that it puts just these are just numbers now, you see. So if you change anything over here, this won't change. So if you do add more wells in here, you have to copy this down. I think there's a new function, a dot function. I saw a YouTube video on it whereby it trims ranges or whatever, so that you don't have dodgy things in your graphing ranges. But that's the only tricky thing to do. You'll find that, so now these are just the values that are looked up from this table, and then you'll find that these cross plots calculate that correctly. Okay, sorry, that was all a bit long-winded, that, wasn't it? Let me get rid of that. Okay, so that's where we are, and the final sums and averages, conclusions, top tips. Okay, don't just use Excel average function. Use the properly weighted averages, especially for net to gross and water saturation. The Excel confidence function gives the range of means for your field or prospect of interest, your population means, not the range of well properties. If you were trying to predict the values, the average properties of your next well, for sure, just use the well averages. But if you're trying to predict the average properties of your next oil field, then use this confidence in the mean calculation. Graphical QC is important. Don't just look at numerical tables. The trends and outliers are important. These QC tables can see if there's anything that needs to be investigated further. If you've got a porosity log that's lying way off the line, or a very thin interval, why is it so thin? Is it faulted out? Is it representative? Do you want to consider removing it from your data set? It's just good to look at trends and outliers, and there'll be more of that in my next video, hopefully. And if you like this spreadsheet, send me an email at the link in the description below, and then you too can sit down with your cup of coffee in a darkened room and try and figure it all out. Okay, that's it. Sorry, I've drifted on yet again. I'm trying to get down to 10-15 minute videos, but obviously I'm not doing too well at the moment. Where am I now? I must be 36 minutes, twice as long. Keep trying, must try harder. Okay, thank you very much for your attention. See you on the next one. More tips and tricks coming up. Cheers then. Thanks a lot.